everyone. Okay, yeah, thanks for coming and listening, everyone. So today I'm just going to be briefly running through some work that I've been doing with Shane and Dietmar at Monash. And so what we've been trying to do is couple a shallow water model of the thermocline depth to the full atmosphere. So just on this first slide, we've just got a sort of little schematic of our overall goal, which is to have this shallow water models thermocline depth anomaly interacting with the sea surface temperatures that the unified model sees, and then also interacting with the wind stresses from the unified model. So I guess, yeah, to start off with, our overall aims on putting this model together has been to try and couple a sort of simple ocean model to a more complex full AGCM atmosphere, really with the goal of being able to perform a bunch of different quite idealized experiments into things to do with ENSO dynamics. So for example, impacts of different SST patterns on ENSO terminations, and perhaps also enabling experiments into things like to do with interbasin interactions. And so, as mentioned, the, I guess, AGCM atmosphere component that we're using is the unified model version 7.3 with a fairly coarse 2.5 by 3.75 degree grid. And then I'll elaborate on this a bit more later, but we're also using some form of background sea surface temperatures from the unified model, and that's coming from either a climatology ancillary or otherwise a slab mixed layer model, which previously Dietmar and his colleagues, I think Claudia Frauen and Yanshan Yu, had worked on embedding into the unified model. And then for our simpler ocean component, we're using a linearized shallow water model of the thermocline depth anomaly, and that's coming from Kolik and Murty. And so this is I guess, yeah, a fairly simple model just with really one layer and three variables. So those variables being U, the zonal velocity anomaly, V, the meridional velocity anomaly, and then also the thermocline depth anomaly. And these three variables are then just linked together with three equations. So we've got a zonal momentum equation where the zonal velocity anomaly is, I guess, impacted by a Coriolis term, a pressure gradient term, and then also a wind stress forcing term. The same for V, and then lastly, those three variables are tied together with a continuity equation. So Shane had put together and been working with for a while a standalone version of this shallow water model, which could be forced by, I guess, any supplied wind stress forcing. And so this standalone implementation had been put together using a 1 by 1 degree grid between 51 south and 51 north. And its sort of integration forward in time was done using a leapfrog time stepping scheme. And I guess one thing to note is that in terms of sort of the, I guess, dynamics in the tropical Pacific, it can do a pretty reasonable job in reproducing some aspects of observations. So what we have here in this figure from a paper by Sonia Nesker and Shane is on the y-axis, we have the warm water volume anomaly, which is, I guess, the integrated volume anomaly of water above the 20-degree isotherm across the equatorial Pacific. And in the gray dotted line there, it shows that warm water volume anomaly from observations, and the red line is coming from the shallow water model forced by wind stresses calculated from the, I think, Era 5 reanalysis. And yeah, so it does a reasonable job in reproducing that evolution. And so now I'll just sort of briefly run through how we set out to try and couple these two models together. So as mentioned a bit earlier, we start with some sort of background sea surface temperature from the unified model, either coming from climatology, which is where this figure shown here is from, or otherwise from this slab mixed layer model that Dietmar had been working with previously. And then we calculate wind stress anomalies from the unified models wind stresses. And using those anomalies between 30 south and 30 north, we take them and also take the current state of the shallow water model and use those wind stresses to, I guess, move it forward one time step. And so that's the, I guess, coupling in one direction using the unified models wind stresses to force the shallow water model. But then we also need some way to couple in the other direction. So we want some way for this thermocline depth anomaly to influence the sea surface temperatures that the unified model sees. And we do that in a fairly simplified way. So basically, at each time step, we calculate a eastern warm water volume anomaly. Basically, we integrate the thermocline depth anomaly over this box in the tropical Eastern Pacific and get its value at each time step. And we basically use this value of this anomaly to modulate a prescribed sea surface temperature pattern on top of the background sea surface temperatures. So we take our warm water volume anomaly, multiply it by some pattern, and then also a parameter, which we'll call a coupling coefficient, and add that result to our background sea surface temperatures to get a final sea surface temperature that the unified model then runs its next time step using. And so, yeah, so that's sort of the conceptually how we set out to put this model together. In terms of actually implementing it and actually putting it together, I guess one option which could have made sense would be to, if we try and go through an external coupler to transfer data between those two models. We opted not to do this, I think, mainly because we didn't really have any experience in using a coupler. And instead, as mentioned, Dietmar had sort of previously had a slab mixed layer model that him and his colleagues had embedded into the source code. And so we opted to try and basically stick our existing shallow water model on top of that and try and get it working. Of course, sort of opting to do it this way also had its own challenges and hurdles that we ran into. So a few sort of technical challenges we came across was, I guess, firstly, working out how to add new prognostic variables to the unified model. I was sort of surprised how involved it was each time we wanted to add a new variable, such as for our shallow water model, like U, V, and eta. It was, yeah, quite an involved process, modifying some quite cryptic different subroutines. But probably bigger issues came from the, I guess, different grids that our two models are using. So the coarser grid for the and the 1 by 1 degree grid for the shallow water model. And then on top of that, the fact that the unified models code was parallelized, where sort of it splits up the global variables onto little patches, and then each processor sort of deals with calculations on each patch and they share information together. Whereas our standalone version of the shallow water model ran in serial using whole global fields, and it wasn't too clear how we could sort of get those two bits of code to be sort of compatible with each other. I guess by pure luck, it turns out that a lot of those hurdles had sort of been dealt with by the river routing model that already existed in this version of the So I'm not too sure of sort of the history of this river routing model, but it turned out that it ran also using a 1 by 1 degree grid in a non-parallelized way. And so that sort of going along with it, it meant the source code included a lot of useful machinery for doing things like creating prognostic variables on this higher resolution grid, and for sort of unparallelizing your variables or collecting them onto a single processor. And it also included useful area-weighted regridding routines that we could use. Um, so sort of schematically, what the river routing model does is it starts off with each of its variables broken into patches spread across the different processes, and uses a subroutine called gather field to glue those patches together into a single global field on a single processor. From there, it runs its, I guess, river routing update and updates all the variables, and then splits them back across the processes. And so, yeah, we were lucky to be able to basically copy this exact structure to try and paste the shallow water model into the So we can start off with our shallow water model variables split across the processes, bring them together all into one, then basically paste in the existing shallow water model code to do a update at a single time step, and then scatter it back across all the different processes. Of course, it took, yeah, I guess a bit of iteration to get it all working. But in the end, it sort of came together. So I guess we've run a few different experiments, just seeing how it goes. And I'll briefly run through a little bit of output from some of those experiments. So first, I've just got a little animation of the model running. So on the top left, we've got that eastern warm water volume anomaly, which is used to modulate the sea surface temperature pattern on the top right. And on the bottom left, we've got the zonal wind stress anomaly, which is then used to drive the shallow water model, whose thermocline depth anomaly is shown on the bottom right. And so, yeah, sort of luckily it ended up running without crashing. And then, yeah, going into a little detail about a few more results from those different configurations. We can look at sort of the, I guess, variance in the sea surface temperatures anomalies or their standard deviations. So those are shown here when we're using the climatological background sea surface temperatures and different values of that coupling strength parameter, which sort of, I guess, amplifies or mutes the pattern. Of course, when we're using the climatological background, it means that all our variance is basically coming just from that pattern. And then this is how it sort of compares to when we've also got the additional slab model running. And I guess a couple of things to notice are that with the smaller coupling strength parameter, I guess the signal in the Eastern Pacific from the pattern gets a bit lost among the I guess slab model's own variants. But even with the stronger coupling strength parameter, that variance in the Eastern Pacific actually is a bit smaller than in the climatological configuration. And that this is just those standard deviations from the Hatters data set for comparison. And we can also just take a slice across the equator to see how those different configurations compare. And then briefly looking to sort of into things like the ENSO dynamics in the different configurations of the model. Here we've just got cross correlations between the Nino 3-4 anomalies and the warm water volume anomalies for that integrated, I guess, thermocline depth anomaly over the equatorial Pacific. I can see it's quite different in those different model configurations. With the slab model in particular, those cross correlations are very symmetric looking and don't really look too much like the observations shown in the black dotted lines. And then also we can also look at things like the Nino 3-4 autocorrelations. And one thing that sort of stands out is that in sort of all our model simulations, the peaks in the autocorrelations are quite a bit narrower than in the real world, which I think, yeah, sort of suggests that the El Nino and La Nina events in the model aren't really persisting as long as in the observations. And I think, yeah, one reason we tried introducing this coupling strength parameter was to try and sort of, I guess, yeah, strengthen that coupling and hope that it would widen those peaks. But for the slab SST background, it doesn't really have that effect. And another sort of, I guess, interesting thing is that in the climatology background, sea surface temperatures and the higher coupling strength parameter, it looks like we almost end up with something of a biannual cycle where it might swap between El Nino and La Nina every year. So I think, yeah, there's probably quite a bit more work and simulations that can be done to work out sort of what the model's doing and what sort of things, what sort of experiments it could be useful for. But yeah, that sort of wraps up where we're at for now. And yeah, thanks for listening. And if anyone has any questions or comments about that, yeah, feel free to go ahead and ask them.
Thank you, Spencer. Yeah, Laurie.
No, I was not. I was just congratulating him for an interesting talk. I don't have any questions.
Thank you.
Yeah, Dietmar.
Yeah, I guess I have questions, even though I'm supposed to be a co-author.
Yeah.
I don't know all the details. So did you say when you connect your thermal time depths to the SST, you add the pattern, or is the pattern added to the tendencies?
So yeah, that's a good question. So it depends on the SST sort of type of background sea surface temperature we're using. When we're using the climatological background, we just sort of, I guess the model sort of finds the climatology at each time step, and then we just directly add the pattern on top of that. But with the slab background SSTs, that slab model is updating using tendencies. And so we then, I guess, yeah, add the pattern, I guess, also using a tendency equation where we look at I guess, the last change in the thermocline depth anomaly and use that to either add or subtract a little bit of the pattern.
Okay, so you use a change in thermocline depths to diagnose a change in SST, right?
Yes, yeah.
Yeah, and your alpha must have a unit. I mean, you are saying you come from thermocline depths, which is meter, to as multiplied with an SST, then the alpha must have a unit, right? I mean,
so I guess the pattern that we were using here was calculated from the observation. It was the, I guess, regression against the sea surface temperature anomaly against the
so the pattern that you have is SST per meter, and then you multiply it with the thermocline depth index, which is meter, and you would get SST.
Yeah.
But then you have to still scale it up by 60% because actually it doesn't work.
Yes, yeah.
Okay.
Yeah, Shobi?
Yeah, I sort of probably had a similar sort of type question to Dietmar's. That sort of how that would be derived. and how widespread it was. It looked like you were mostly putting south to 40 north. And the other sort of questions obviously was the fact that you were showing this sort of biennial response, and whether that was linked to the shallow water model, or whether that's in any way inherent to what we're currently seeing, what we see in our couple model. I mean, whether that's just because the shallow water model hasn't got the freedom of movement to do anything. You said at the start you were going to look at interbasin variability as well. I mean, I guess that's somewhat down the track when you've got the Atlantic. I don't know if you've got Atlantic variability going on at the moment, or you've just got Pacific variability you're focusing on.
Yeah, sorry. I missed the first question.
I think the first question was similar to Dietmar's about
how
you were driving that pattern on the SST.
Okay, yeah. So I guess about the biannual response. That's something I'm not too sure about, whether that's coming from the shallow water model, or whether it's sort of to do with the UM, and then with the interbasin interactions and stuff, it's not something we've actually started looking at yet, but I think have the goal to look at down the line. Thank you.
I have some initial thoughts on the biennial response if we have time quickly. So I suppose when you showed the plots, Spencer, with the lead lag relationship with warm water volume and SST, it seems to suggest that the warm water volume doesn't really influence the sea surface temperature, so it doesn't have the typical. So normally what happens during an El Niño event, you discharge warm water volume, that leads to a change in phase. And it seems like basically what the model's showing is the warm water volume follows the sea surface temperatures, but it doesn't ever lead the sea surface temperatures like in the. So I suppose a little bit of me wonders whether maybe what we're seeing in the biennial nature is driven solely by the atmosphere, because it doesn't seem like the ocean dynamics are represented well. But I need to think more about it and look more into it, I think. It was a really interesting question, and it was really nice presentation, Spencer.
Yeah, David.
Yeah, thanks. Look, I just wanted to say I was really impressed that you managed to build in this shallow water model by borrowing code structures from the river routing. I think that's very innovative, and make sure that you make this available, through GitHub or somehow, like make it sort of out there for others, because I think it's a really great trick.
Oh yeah, sure. Thank you. I think that should be something we can do. Yeah, that sounds like a good idea.
It's been extensively noted in Bitbucket, each thing. So there's lots of notes around how every step's been done. So yeah, Spencer's done a fantastic job.
Yeah, Dietmar?
Again, a question to what Jane just said about the cross correlation between SST and thermocline depths, because Spencer, you didn't show that for very long. Can you show that again?
Yeah.
While I was talking, I was having mental images of the figure, and then I kind of started to doubt my own response.
So this one, I think.
So in the slab ocean, the thermocline depth has a bit of a lead of a day, a month or two or something, right? Or
I think so, yeah.
So the right figure. So because otherwise, I mean, how would you get a pattern if the slab ocean? I mean, in the slab ocean, you don't have this an in pattern without the shallow water model. You showed this in your standard deviation map, right? So it must have an influence, and therefore it must have a lead correlation, right? But the lead correlation is really way too short, right? It's just 1 or 2 months instead of maybe 3 or 4 or 5 months, which you would need to have.
So in the more recent period, Dietmar, like since 2000, the lead time between warm water volume changes and changes in SST is much shorter. And it's kind of
but not this short, right? I mean,
it's kind of not too much different to that.
Mm-hmm.
So it's 2 to 3 months if you just focus on this relationship between 2000 and 2020. And what it kind of suggests is basically the warm water volume is just driven by kind of westerly wind bursts. Yeah, I don't. I need to think more about it. I'm going to stop talking.
I mean, it looks kind of good in the where you have only your shallow water model and not the slab, right? I mean, that actually doesn't look too bad. Just way too simple and way too strongly related, but that's clear because there's nothing else going on.
That was the figure I was looking at. Sorry, I must have got confused. When you were talking just then, I was looking at the figure on the left, not the slab one.
Yeah, no, but the right one is the one.
Mm-hmm.
Yeah, maybe related to David's question with the model development. I also think you did a fantastic job on the development, but I would like to ask a few questions to maybe highlight the model developing strategy. So you use the fairly low resolution model. So how many years of running did you had to actually get to what you think is your final solution? To get a bit of an idea of how much development is actually in there. You probably have run it 100 times or something, right? I mean, and then always run it for a few years, right? Or
yeah, I think so. I think yeah, it was very much started off with just like working out how to change things in the UM code and just changing little things and then adding one variable and not really putting the shallow water model in, and then slowly, I guess, building up bit by bit. But I'd probably say maybe like there are probably maybe 15 to 20 steps or so, I think, of adding things to get to the final one.
That's pretty good. And for each step, you have to run it for several ENSO cycles, or what? How long do you usually typically run it?
I guess, yeah. So initially, before we had the actual any shallow water model thing, any shallow water model embedded into it, I was just sort of working out how it works. I guess it was much shorter simulations, and probably as I was working on it, I think the main thing I was concerned about was would it crash or not, or was it crashing or not? And that usually during that development, I probably just run it. I wasn't looking so much into these sort of ENSO relationships yet, but I'd probably run it for 1 to 3 years each time.
And in terms of what Aidan or others are interested in, that you make this public and other people can use it. I mean, the problem is that you have implemented this in a version of the Access that nobody uses. Right, so I wonder to what extent can this work that you have done be used in a way that it actually lives on in the next generations of Access models. And I have my doubt a little bit about that, right? Because I feel like you have developed it into a dead end model, right? I mean,
right. Yes. So this is using a version of the UM that uses the UM UI, which I think, yeah, isn't really being used anymore. In terms of
but it's 7.3. Sorry, it's 7.3. So that's the one that's in Access ESM 1.5. And can I ask Aidan, do you know or Martin, which version of the UM is going into Access 1.6?
It'll still be the same version of the UM.
Okay, so it's really just the resolution.
Yeah, there might be some changes to cable.
Okay.
It'll basically be the same UM.
So if Spencer's model can transfer from N48 to N46, sorry, N96, then potentially it could be used as a tool to augment Access ESM simulations, right?
Yeah, it should be able to be carried across, I think.
Yeah. Anyway.
That's the sort of thing that a working group should pass up to the SAC. There's a SAC meeting this afternoon. That would be, if that's a useful research tool, then that's something that you should say that you want.
Well, I haven't played very much with atmosphere only runs, but I think it is a really good tool if we, if we can take an Access ESM simulation, say, because there's lots of us working with Access ESM, and branch off into atmosphere only runs, which can do interesting forcing, which we impose, let's say from Spencer's configuration or something else. But it is useful sometimes to be able to decouple. So yeah, I think that could be very useful.
But just a quick question then, is it much faster and much less expensive than ESM?
Good question. So I think
Yes, I mean, the answer is yes. I think it's about between 50 to 100 years in optimum, I think. And it uses only, I don't know, much fewer CPUs, right? I mean, how many CPUs?
yeah, so these runs we were doing 50-year runs, we would use I think 3 KSU for each 50-year run.
And you say 50 years would run in a day? Is that what you said, Dietmar?
It used to be like that. I mean, we used to have this that it runs 50 years a day, but I haven't run it for a long time. But it was something, I think in some configuration, we had the low resolution atmosphere model running 70 or 80 years a day. But I don't quite remember what kind of configuration that was, but that's what I remember.
What did you find, Spencer?
I think a bit like between a day and a half for each one. Yeah.